Inequations and inequalities. And there actually is a subtle difference between the two. Okay, so an inequation is a problem where we're trying to find a set of possible values. And so it has a solution, if you like. So something like this. And a very simple one, of course. This is an equation. So 5x plus 3 is less than 2. We're saying, hey, this is a fact. 5x plus 3 is always less than 2. Can you tell me for what values of x it would be true? Okay. And then we just go solve it like an equation. I go, oh look, oh yes, well, as long as x is less than minus 1/5, 5x plus 3 will be less than 2. So types of inequations, the linear ones obviously are quite simple. Quadratic ones, we have to be careful. So we get our quadratic, and we know with an equation, we'll say what multiplies together to give, adds together to give. That doesn't change, we still do that. This is of course where it's different. With an equation I would say, oh, either x is equal to negative 6, or x is equal to 1. And that would be correct for an equation. However, it is not true to say, oh, either x is less than negative 6 or x is less than 1. That would be not true. Because essentially, if it's less than 0, two things multiplied together, it's going to be negative. I know one has to be positive, one has to be negative, things like that. So way I tend to do it, whether or not I physically draw the graph or think of the graph, is I actually go to a graphic solution. And I think what this is really saying to me, I've got a parabola. I'm only really concerned about two things with the parabola. Its concavity and where it cuts the x-axis. So it cuts the x-axis at negative 6 and 1. The solutions are not included, so I'll circle those. And I know it's a concave up parabola. And so essentially, in my mind, what I'm saying to myself is, well, for what values of x will the parabola be below the x-axis? Well, it'll give negative values. And I can just look at the graph and read off it. Now, it's for the bottom section of the parabola, but of course I'm only interested in the x values. And so the x values would be the ones in between minus 6 and 1. So there's my solution. X is in between minus 6 and 1. I guess the key with an inequation, not just a quadratic inequation, is to find what we call the critical points. That boundary where it changes from positive to negative. And then we can always just test. We don't have to draw a picture. I could have done the same thing by finding, okay, minus 6 and 1 are my critical points. Let's pick an easy number to try, 0. If I sub in 0, I get negative 6 is less than 0. It's included in my solution. So I must be between the two. So the key really is finding those critical points. Personally, when I get one like this, the first thing I do is multiply both sides by negative 1, because I hate factorising negative quadratics. It's just a thing. I don't like it. I just think it's easy to have a positive quadratic. So multiply together negative 4, add together negative 3, positive 4 minus 1. So again, I'll go over. There's my two critical points. This time they're included because it's an equal to as well. Once again, I've got a concave up parabola, because I'm looking at my new equation. If you go back to the first equation, then of course it would be a concave down parabola. But the way I'm looking at it, I'm saying, hey, when is this parabola above the x-axis? So for what x values? So this time I'm on the outside. So a solution to a quadratic inequation will always be one of those two. I'm either going to be in between the 2 points, or I'm going to be on the outside of the 2 points. It has to be one or the other. So a quadratic inequation is something you could be asked in 2-unit. I say 2-unit people look at that. This next one is an extension question. So you won't see one like this in a 2-unit paper, but I can almost guarantee you'll see one come the HSC in a 3-unit paper or an extension 1 paper. In equations where the pronumeral is in the denominator. Now, of course, this is probably the simplest sort of one I can think of, where it's simply x in the bottom of the denominator. And the temptation is to simply turn both sides upside down, and when you do that, you change the sign and you come up with a solution: x is less than or equal to 3. And that is wrong. Okay? Now, the way I do it is I want to locate those critical points. Now the key point, the one thing we're not thinking about here, is fractions. Bottom of the fraction can't equal 0. This will create another critical point. So the bottom of the fraction can't equal 0. So x equals 0, or not equal 0, however you want to say it, is going to be a critical point. Okay. It's going to form part of the solution. Then I actually solve it as if it's an equation rather than an inequation. So 1 on x equals 3, x equals a third. They're my two critical points. So again, whether you do this in your head or whether you physically draw it. So there's my critical points, 1/3 and 0. Oh, rats. I always like using 0 as a test point because it's such an easy number to substitute in. But I can't for this one. So I'm going to pick a different test point. I wonder which one I used. -1 on the left-hand side of 0. Sub it in, I get... No, -1 is not bigger than 3. So logically it says it's going to be in the middle, but let's just double check. X equals a quarter. 1 over a quarter is of course 4. Yes. So alright, I am in the middle. But just to triple check, let's go on the right hand side and test x equals 1. 1 is no. So a bit like the quadratic one we just saw. In between the 2 points, outside the 2 points. Now, the reason for that is the most common way of solving these, which perhaps some of you have seen, is to multiply both sides by the square of the denominator. And the reason you multiply by the square of the denominator, if I was just to multiply by x, I don't know whether x is positive or negative. So I don't know whether to change the sign or not. But if you multiply by x squared, you know that's positive. So that's why people use that technique, and you end up with a quadratic inequation. So hence why the solution, again, is either in between the 2 points or on the outside of the 2 points. I say that is the most common way of doing it. The most successful way of doing it is this method. Okay? I have marked this many times in the HSC, and without fail, this one is the most successful way of doing it. Despite what your tutors may have told you, despite what the textbooks say, this is just so much easier. Okay? So all you're doing is having a look at the bottom of the fraction and saying, hey, what makes that equal to 0? Solve it like an equation. You've got all your critical points. Usually there's only 2, but you never know. It could be a fancy one. And you just test and see where you are. So there's my solution. 0 is less than x is less than or equal to 1/3. So let's try this one. Bottom of the fraction. Okay, I know -3 is going to be a critical point. And now I just solve a very easy equation. Because I don't know about you, linear equations are easier to solve than quadratic equations. So another reason for doing it this way. And we get -13 on 5. I now know my critical points. Where am I? Well, if I test 0, we'll find out that 0 is included, so I know I'm on the outside. So there's my solution. X is less than -3, or x is greater than -13 on 5. So I said there was a difference between an inequation and an inequality. So what's an inequality? Well, an inequality is a problem that we're trying to prove is true for a known set of values. See, the first one was an equation where we were trying to find the set of values. We're saying, all right, for what set of values will this be true? Whereas an inequality is, these are the set of values, prove it's true. So sort of, if you like, the opposite. Very technical. And often we use the wrong word. You'll see people call inequalities inequations and inequations inequalities. But technically, that is the difference. Now, how do we do it? Well, it's a proof. It's a proof. So we usually set it out like an identity proof. So what I'm trying to do is, after you're stating what it is that you're trying to prove, once you've decided this is what I'm going to prove. Now, sometimes people like to rearrange what it is they're trying to prove because they think, oh, this will be easier. Now that's fine, but once you've decided upon what it is you're trying to prove, you have to remember it is not an inequation. You can't solve it like an inequation, okay? If you wanted to prove the left-hand side is less than the right-hand side. A lot of people like to do this. They'll start with the left-hand side and then try and show that, hey, I can come up with some expression which is always less than the right-hand side. Some people, this is a very common idea, because 0, it's so much easier to show something's always positive or something's always negative, because then you can play with squares and things like that. So rather than start with the original inequality, and that's what I mean, before you decide on what you're going to prove, you might want to rearrange it, and you might say, no, I'm going to, instead of proving the left-hand side is less than the right-hand side, I'm going to prove the left-hand side minus the right-hand side is always less than 0, so is always negative. And then go and prove that. Because once you've proven it, it now becomes a fact. And once it's a fact, then you can move terms from side to side. But it's not until you know it's a fact that you can do that. Now, a third alternative. Sometimes we just can't link the left and the right, obviously. So what we do is we start with the left-hand side, we manipulate it into some new expression, and we go, nah, can't see where that's heading. So then we go to the right-hand side, and we manipulate that, and then you go, oh, hang on a sec. What I've proven here on the right-hand side is actually always bigger than what's over here on the left-hand side. So therefore, logically, what I started with must also be. So that's an alternative way of doing it. Right, so you'll come up with a new left-hand side is less than a new right-hand side. So from that you can logically conclude then, oh okay, well then the original left-hand side must have been less than the original right-hand side. So let's have a look at proving something. How do we do it? Sometimes start with a known result. So it might be something that's obvious, such as a square is always positive or something like that. It might be a bit of information that was given to you. So starting with a known result. So in this case, it's a very simple little one. If we know x minus y is always greater than y plus z, they want us to prove y is always less than x minus z on 2. So I'm going to start with the known result. They told me x minus y is greater than y plus z. Now, because this is a fact, I can manipulate it because it's a known result. So really this one just involves making y the subject. So as I say there, you can only move terms side to side when you're doing a proof if it's a known fact. So minus 2y is greater than z minus x, and bang, make y the subject, it drops out quite nicely. So that's the idea of starting with something you know to be true, and then you can manipulate that to show the result that you want. The idea I was talking about before, where we'll move everything to the left and show it's always positive or negative. Now, we're told that A is a positive number for this, or 0. B is a positive number, or 0. We're going to prove that AB outside of A squared plus B squared is always greater than or equal to 2A squared B squared. So you sort of look at that and you go, oh geez, start with a known result. Well, all I know is A and B are positive. That really doesn't get me that far. So I'm going to just start with an algebraic expression. Notice there's no inequality sign there at all. I'm just saying, hey, here's a piece of algebra. This piece of algebra, I'm going to try and attempt to show it's always positive. Alright, well, let's expand it out. It's equal to that. You'll notice a common factor there of AB, but have a look inside the A squared minus 2. Well, hang on, that looks familiar. That's A minus B all squared. Well, we know the A minus B all squared is positive, and we were told the A and the B are positive, so actually it's fair enough to say that that is greater than or equal to 0. So now I have a known fact. I know that AB outside of A squared plus B squared minus 2A squared B squared is always greater than or equal to 0. Because it's a known fact, I can now move the 2A squared B squared term to the other side, and I get the required result that they want me to prove. Now remember, these are the sorts of questions where leaving room on the right hand side here is quite handy, because sometimes you might want to explain yourself. You know, I didn't bother saying, oh, because we know A is greater than 0, B is greater than 0. But sometimes people like to write that because they think, hang on, how can I claim this is always positive? Well, fair enough, the square, but how can I claim the A and the B part? Similar idea, sort of combining the two. We start with a known result, that known result being that the squares are always positive or zero. It's a very handy thing. Here is a classic inequality. Show that if A, B and C are always positive, then A squared plus B squared plus C squared is greater than or equal to AB plus BC plus AC. It's actually quite a common little question. And I'm going to start with a fact. And that fact is that A minus B all squared is greater than or equal to 0. I know that to be true. Now if I expand the left-hand side out, and because it's a known fact, I can manipulate it, I get that A squared plus B squared is greater than or equal to 2AB. But hey, A and B were just pronumerals. I could have picked any letter I like. So if that's true, A squared plus C squared must be greater than or equal to 2AC. And B squared plus C squared must be greater than or equal to 2BC. They're just letters, or symbols I'm putting in there. Well, if I now look at this and treat it like three simultaneous inequalities, then add down, look what happens. I get 2A squared plus 2B squared plus 2C squared is always greater than or equal to 2AB plus 2BC plus 2AC. Divide by 2, we have our result. So A squared plus B squared plus C squared is always greater than or equal to AB plus BC plus AC. This last bit that we looked at possibly is more extension 2. We don't see a lot of them in extension 1. But, you know, book's got some nice questions on it, so why not have a look at them? And it's a nice little taste